rethink. So let's look at this theorem that says basically V and W are vector spaces that are finitely generated over field F. Dimension of V, that means the number of elements in the basis of V, let's set that equal to n, and dimension of W, let's set that equal to m. As we see, these letters correspond to the commonly used letters in the dimension of a matrix. Then we have that home of VW, and home of VW basically is the set of all linear maps from V to W with the usual operations. Is isomorphic, so this symbol, to F to the m by n, so all matrices m by n over the field F, over some field F. All right, so the proof of this, so this is a very interesting theorem, right? And the proof of this is we choose basis for V and W, so, and define this map from the set of all linear maps between V and W to generally matrices m by n over field F by the relationship that F is sent to the element which is the matrix of a map between the bases B and C. The map is injective, and that's because every linear map is clearly defined by its matrix in respect to B and C. And the map is onto F to the m by n, so onto F to the m by n, so all matrices over F of dimension m by n, because every A in this set, so any matrix in this set is the matrix of some linear map of some let's use this Greek letter, some linear map between V and W. All right, so any matrix can be seen as some particle linear map like that. And we need to check it is linear. All right, so you can of course do this more closely, but let's realize we need that FG, so some two linear maps from V to W, and some C that ranges inside the field F over which we have it all. For these, we have the following, that C times the map F, all of that in respect to B and C is actually the same as if we take out the C and do F, B, C. That's first thing. So now we see this matrix that defines the map in respect to these bases is treated like a vector so far, right? So this is all a vector space of all the maps. And if we add two maps, F plus G, and do them in respect to B and C, well, we also need this property to be satisfied. This closed under addition. So because that's fine, we can actually do this by more steps, but we skip that in order to have it written in a shorter way. But anyway, here is sort of the outline of the proof of the initial theorem. And the theorem, just to reiterate, stated the following: that V and W are two vector spaces over a field F. And the home of V and W is defined as the set of all linear maps between V and W, from V to W, with the usual operations, the vector spaces over F. And then that set that we just mentioned is isomorphic to matrices m by n. So we proved it using the following way.